Welcome to Lecture 10. So far we've been talking about models after models in game theory. For each of the models that we have introduced, we've laid out the actions, the strategies of the players, as well as the outcomes of the game, and how the payoffs are distributed. And very importantly, we talk about solution concepts, basically different forms of equilibria concepts and property of these equilibria in games. In particular, in the last lecture, we talked about repeated games. It seems like a suitable model for us to capture agents who are engaging in some sort of iterated interactions in the same environment, where the outcome of the game is determined by the collective behavior of the agents. And if we look back at the original intention, is really to develop theoretical foundations for multi-agent systems. And if we view these players in the game as rational agents, one of the very important dimension that we need to take into account, and we haven't really talked about, was learning, right? And learning, as in any forms of artificial intelligence disciplines, is a very crucial topic. So the reason is that the capacity to learn is really a key facet of intelligent behavior. So in any sort of AI system, you would imagine that the agents should have some capability to adapt through the interaction with the environment. Right. Of course, when the environment becomes a multi-agent system, so there are more than one agent in the space, the task of learning also becomes more complicated. There are more issues that came up which were not present in the single agent case, right? Especially now, the agent would not just learn through the interaction with the environment or through some input signals, but also the agent would learn by repeatedly interacting with other agents. And this can be quite important for multi-agent systems. First of all, if you recall, all the models that we have introduced in game theory, we were predicting what's going to happen in the game using the notion of solution concepts. As we define the different forms of equilibria, and we say that the outcome, according to our assumption of rationality or sequential rationality, will be that outcome as specified by the equilibria. However, in nowhere in our discussion I talk about how did the agent actually arrive at those equilibria. I'm just given the state, I'm saying, okay, what will be the outcome? But obviously, if you consider in a multi-agent system, when the agents are performing their actions in the space, the outcome should be the result of certain dynamics among the agents, and also interactions between the agent and the environment. This means that the process that lead up to an equilibria state in the game should be some sort of a learning process. Right? The agents will interact with each other repeatedly and adapt their behaviors correspondingly. So this is exactly learning, right? But we haven't really talked about how did the agents learn in order to reach these specific equilibria states. Also, very, very importantly, is that, like what I said in the very beginning of this course, one of the key characteristics of a multi-agent system is that the agent do not have full knowledge regarding the environment. And this means that the agent would not know, for example, everything about the game setup, the opponent's strategies, their opponent's preferences and beliefs, and so on. And through the playing the game, the agent would need to gain such knowledge during the course of play and adapt their behavior. So this means that we will there's a need for us to specify algorithm, essentially mechanism that allow the agents to acquire such knowledge and update their knowledge and belief along the way, right? This is a crucial aspect of artificial intelligence. Thirdly, most of the cases would like the agents to adopt some optimal ways to play a game, right? This is like developing a chess playing algorithm aiming to beat other players. It could be simulated artificial agent player, or it could be actual human being who are playing this chess. And we want the agent that we developed improve the performance, improve the ability to perform the task. Right, and because of the game setup is complex, it is typically not easy to use a rule-based system to fix the behavior of the agent, and therefore learning provide an opportunity for us to implement agents that will self-adapt and eventually arrive at a very good status in terms of its ability to play the game in an optimal way, right? So that's the reason why learning is so important in a multi-agent system. Of course, we will need to be more specific of what we mean by the task of learning. A learning rule refers to an algorithm that facilitates an agent to learn from the history of a play and adapt its strategies. And essentially, what we are interested in is such algorithms. The multi-agent learning problem can be approached from different angles. Right? Particularly, there are two main goals that could arise when people are interested in studying learning. One is the descriptive goal. This is more in line with psychology or cognitive or behavioral scientists who are really interested in how the world evolve, how human or animals or economies, organizations, and so on, they are doing what they're doing now. This has to be a process of adaptation, evolution, and the reason for learning, for developing learning algorithm is so that we want to explain the behavior that we observe in the natural world. So this is more of a descriptive study. Also, we have another very important goal is more engineering focus, is more prescriptive. This is to investigate the ideal way for an artificial agent to improve themselves in playing games. And this could be, developing the best chess playing algorithm in the world, or developing some sort of bots that are able to place bits on the internet and so on. So all of these requires a learning algorithm that enable the agents to reach and sort of an optimal state, right? To gain capability along the way. Not necessarily explaining how actual humans learn, but it's just a way that achieves optimality in engineering tasks. So mostly, we will be talking about more from a prescriptive side without entering too much of the descriptive side, because in the descriptive side is requires knowledge from not just computational aspects, but also a whole range of other fields, which I would not elaborate. So, and before we actually go on to present any learning algorithm, I also want to compare, well, not really compare, but to point out some of the key differences of learning in a multi-agent system from learning in general, right? So by learning in a multi-agent system, we're really talking about, we have a game and there are players in the game, and we are developing some algorithm that's learning rules for players in the game that specify how they would repeatedly interact with the opponents. Right. So imagine we have a situation where we have two-player games, and the payoff matrix is described in here. We have two actions for each player, and if you analyze this game, you can find that there is only one Nash equilibrium of this game, namely BL. Right. However, you can see that there's another outcome TR, which is more desirable for either player, right? And from the standpoint of player 2 or player 1, for example, imagine that player 2 is a learning agent, right? So in this way, there's a possibility that we could, for example, enforce a behavior that's not Nash equilibria in the stage game, but it's a behavior that we want. For example, if player 1 can somehow convince player 2 to believe that it will always choose T, then player 2 can start responding with the action R, and the game will stabilize at the outcome T and R. So in this scenario, we have a learner, which is player 2, and we also have a teacher, which is player 1, and player 1 can somehow influence player 2's decision through making decisions on itself, right? That is very interesting, that in a multi-agent system, not only an agent can play the role of a learner, but also can play the role of a teacher. Right. If you look at a second example, this shows that learning may not seem as rosy as it seems. It's sometimes when you are a learner, you would not be performing at a better action than if you were not a learner. Right. So imagine this case, it's a famous game of chicken. So we have two players, and each of them has two actions to choose from, yield or dare. If they both yield, then they walk off with payoffs 2 each. If they both dare, then they this incurs a high cost to each person, so they get only 0 payoff. But if one dare and the other person yield, the person who dares has a payoff of 3, and the person who yields only get a payoff of 1. So that's not very desirable for the person who yields, right? And there are actually two Nash equilibria in this stage game. We have yield there and there yield, right? So these two off-diagonal outcomes are the Nash equilibria. So this means that in the Nash equilibria, one of the person will need to yield, and the other person would dare. Right. Suppose player 1 is not a learning agent and just simply play dare all the time. Right. And also player 2 is a learning agent. So in our intuition, if you have the ability to learn, it should give you an advantage over the person who do not learn. But this is not the case here, because in this case, after a while, when player 2 realized that player 1 will only choose to dare, then player 2, being rational, will choose to yield, right? And that means that player 2 will receive lower payoff than player 1, right? So the ability to learn really doesn't help player 2 too much in this sense, right? So in conclusion, I'm not actually making any concrete claims for now, but I want to just use these two examples to illustrate how sophisticated or there are some profound challenges to the whole issue of multi-agent learning. In particular, an agent should consider how to influence the future behavior of the opponents, as well as how to consider how the opponent will influence themselves. So the agent is both a learner and a teacher at the same time. And we are going to, in this class, discuss learning in repeated games. Right. So we're faced with a two-player repeated game. Right. The two players are 1 and 2, and we have this discount factor delta. So consider a history of this repeated game, which is specified as a finite sequence of strategy profiles, A1, A2 up to AT. And if we fix an arbitrary player, it's either 1 or 2, the empirical distribution of the opponent J, you can see that if I is 1, then J is 2. If I is 2, J is 1. So the empirical distribution of that J at the particular history H is a probability distribution over the actions of the opponent, and it essentially computes the proportion of stages so far that has happened in the history that the player J has adopted a certain action A. Right, so formally speaking, we define Pj of A, so that's the probability as a fraction of Wha divided by T, where T is the number of stages that have taken place in the history, and Wha is a weight, and it's the number of stages, during stage 1 up to stage T, in which the player has played A, right, in those stages. So that's sort of counting the frequency of the agent adopting the action A. Right? As an example, suppose we have this prisoner dilemma game, and this is an iterated form of this game. And suppose at history H, the opponent has played the actions C, C, D, C, D, C, 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 D, D, right? So there are 10 stages that have taken place so far. Then the empirical distribution is a distribution over the two actions C and D, and C will have a probability of 60% because in the history, player 2 has adopted C 6 out of 10 times, and has adopted D 4 out of 10 times, so the probability of D will be 40%. Okay, so that's really just nothing. It's just counting how many times the opponents have adopted certain actions. And to describe the learning algorithm, the learning rule called fictitious play, we basically make the following assumption. The opponents, basically they are quite, we assume that the opponents are in fact not very strategic, in the sense that they are strategic only at the level of a stage game, rather than thinking about the entire dynamics of the repeated game. The opponent would just play the game according to some sort of stationary strategy. Remember, a stationary strategy is a strategy where the agent does not really change through the stages. Say, the strategy could be, of course, a mixed strategy on the stage game. So it could play sort of like a 0.6 of a certain action and 0.4 of another action. And that's you can see that's a fixed strategy. It's a fixed strategy for the static game. And if the player in every stage it plays this mixed strategy, then this strategy is called a stationary strategy. Right, and then we assume that the opponent's play would essentially correspond to such a stationary strategy. More formally, it's a sequence of IID, so independent and identically distributed multinomial random variables with a fixed but unknown distribution. Right. So the key thing is the fixed, because this means that it's a stationary, and unknown means that we don't know about the mixture of actions that's adopted by the opponent. And of course, our goal, if we make this assumption, if indeed the opponent is following this stationary strategy, our goal will be to discover the unknown mixture of the actions in the stationary strategy, right? And we implement this rule, which is called empirical distribution learning rule, and also known as fictitious play, but I like to call the former because I think it's more giving out the essence of this algorithm. So essentially, it's just trying to learn the empirical distribution. And it is using the empirical distribution to approximate the hidden and then the true distribution that are adopted by the opponent. Right, so we have the protagonist player I. That's the person who is learning about the opponent, and we assume that the opponent is just playing according to some fixed stationary strategy. Then the protagonist player will maintain the empirical distribution as a sort of a belief or estimate about the opponent, and the protagonist player will follow the following procedures. First of all, it will play a best response to the current belief in the next stage of the game. And then, of course, when the players enter the next stage, the protagonist player will be able to observe what the opponent has chosen in that stage, and then that action is fed back to the belief of the learning agent for the belief to be updated accordingly. So conceptually, we have this picture. We have infinitely many stages, starting from stage 1, 2, 3, and so on. Then we have the two agents. There, on the left-hand side, we have the protagonist. On the right-hand side, we have the opponent. At every stage, each of them will choose an action. And, of course, the protagonist maintains some sort of belief about the opponent. And the action, of course, a reflection of this belief. And once the actions are chosen, then there's a reward that's giving back to the protagonist, and also another reward be given back to the opponent. But into the second stage, the opponent's action in the first stage will be used to update the belief of the protagonist agent. Right, and once the belief is updated, then according to the new updated belief, the protagonist will choose another action, and this combined with the action of the opponent, then it will derive a reward, and the same procedure is repeated in the next stage and all the way on. Right. So how does the belief is actually updated? We're just using a very simple sort of counting method to calculate the empirical distribution of actions of the opponent. So the algorithm itself is incredibly straightforward. The input would be just a description of the stage game that is assumed to be visible by both players. So in particular by this learning player. Remember, this learning rule will specify how one of the player will update its behavior through arbitrary number of interactions. So the output would be a mixed strategy sigma for our player I. So what we do is we first of all have some sort of initial belief about the agent. So we assign some initial value to every action of the opponent. So this would be a weight function wj that's given a real number to every action of the opponent. Right? And then we enter in this loop. We keep a counter t initially set at 0. We enter this loop. Within every loop, it will be one stage of the game where the agents interact with each other and getting the reward. Right? So what we do is we look at, we first of all compute the probability of our believed probability of the opponent choosing any action. Right? This can be calculated by taking Wj of A and dividing that by the sum for all of the possible action of player J and the corresponding weight of all of these. So that basically that will be a sort of like a normalized proportion of weights that are taken by the action A. So that is what we assumed as the probability that player J will choose A. And with this, essentially it laid out a mixed strategy of probability of the opponent player J, right? So with that, we can compute a best response to this mixed strategy Pj, right? And call this best response sigma. So after this computation, the players would then enter the next stage game where our protagonist player I will play the strategy sigma because that's the strategy that he believes will be the best response to the opponent for now, right? And then after this, playing this game, we will be able to observe the opponent's actual play, right? Which is some action AJ. It could be that this is the same action as we predicted, or it could be a different action, right? But once we have that action, then we can increment the weight of that action by 1. So basically we're counting up that action, right? And then we increment t by 1. So now the counter is increased, and then this finishes this stage. So once again we finish, once again we start another stage and we do exactly the same thing repeatedly. So you can see that if indeed the opponent is adopting a stationary strategy, this means there's a fixed mixed strategy that the opponent adopts for the stage games, then the empirical distribution of the actions would tend towards that particular mixed strategy. So that's why there's some validity to this sort of very simple fictitious play learning rule. Right. Notice also that the description that I gave is not full. So it does not really contain all the detail that you need to implement the algorithm, especially how do we select the initial weight function. That's not given to us. It could be that the agent is just randomly guessing some sort of weights, or it could be that this weight is given by someone else, or it could be that this weight is somehow obtained through past experience in some other means. So this has not been really fixed, and typically we just assume that we are given this initial weight function. And also how to compute the best response sigma to the mixed strategy. I mean, there are a couple of ways to do that. Of course, we have learned one way, but we assume that this can be done because we're looking at only finite games in the stage game. So now the question is, does the stationarity assumption make sense? In other words, what can we say about the long-term behavior of the players if they both follow fictitious play? And if both of the players follow fictitious play, we call this self-play because it's essentially the agent playing with itself, because they're adopting the same strategies. In particular, we're interested in what we call steady state. So this is a counterpart to equilibria concepts, right? And equilibria is what we predicted as the outcome of the game that the player will eventually reach. So when they reach this state, no one should have an intention to deviate from the current action. And this means that the game essentially stabilizes. Right. And this means that the game has entered what we call a steady state. A strategy profile A1, A2 is a steady state of FP. If it is the case that whenever A is played at stage T, it is also played at stage T plus 1. So once we have A1, A2, then we're always going to see A1, A2 forever, right? This is what we mean by a steady state. And we are actually interested in what are the steady state of the game if the players are playing this self-play in FP, right? And there are actually, we can theoretically come up with a characterization of this, or at least partial characterization of this, but we'll need to introduce some key concepts. So suppose in a normal form game we have a strategy profile which is Nash equilibrium. It's called a strict Nash equilibrium if no player can unilaterally switch to another strategy without reducing its own payoff, right? It doesn't really care about the opponent, but just caring about itself. If it can switch to another strategy without reducing its own payoff, then it's called a weak Nash equilibrium, right? So what do I mean by this? If you look at these two examples, the first one is a PD game. We can see that DD is a Nash equilibrium. That's the only Nash equilibrium. And if at that point one of the player changes his strategy while the other player does not change, you can see that this player will have a strictly worse situation. So it has a worse payoff. And in this sense, in the PD game, that outcome DD is a strict Nash equilibrium. On the other hand, we have another game which is on the right. You can see that TR is a Nash equilibrium, but in this case, suppose you have player 2 changing from R to an L, right? This will give us an outcome of TL, and the payoff to player 2 is not affected. It is in fact still 5. So this means that this TR is only a weak Nash equilibrium. Right? So why do we distinguish the Nash equilibria from strict ones to weak ones? Is that we will need such distinction, we need such a classification when we characterize steady states in any fictitious self-play. Right? So if a pure strategy profile is a strict Nash equilibrium of the stage game. So if we analyze the stage game and the stage game has a pure strategy profile that is strictly NE, then that pure strategy profile will be a steady state of fictitious play in the repeated game. Right? So it shows that, if we use a fictitious play and suppose the stage game has a pure strategy, strict Nash equilibrium, then that will be the eventual outcome of this process, right? So this is saying that the learning rule actually makes sense, right? Actually makes sense, at least for this scenario when there is a strict NE in the stage game, because that will eventually be the outcome as we predicted. What about the other directions? So suppose you have any outcome of the fictitious play, which is a steady state, isn't necessarily a Nash equilibrium, so the other direction also holds. So if a pure strategy profile is a steady state of a fictitious play, this means that after a while the players will just fix on these actions forever, then that pair of actions will be a Nash equilibrium in the stage game. And it's possibly a weak Nash equilibrium. It doesn't have to be a strict Nash equilibrium, but it would definitely be a Nash equilibrium, right? So this shows that indeed that this fictitious play is a way for us to achieve Nash equilibrium, in a really achieving the dynamics that lead up to Nash equilibrium of the game. Right? How are we going to prove it? I'm going to describe the proof. The idea is quite simple, but don't be confused by those extra symbols. They're just there for technicality reasons. So suppose you have A1, A2, which says this is proving the first part, where suppose you have A1, A2, which is a Nash equilibrium. And we want to show that it will be a steady state. So how do we do that? Well, suppose A1, A2 is played at a certain stage T, right? According to the description of fictitious play, when this action is played, it means that this action will be the best response to what is believed to be the opponent's strategies. Right? Now let's consider what will happen in the next stage. To do that, we need to consider the belief of player one, and belief of player one actually is about player two, right? So essentially, player one will maintain this function P, this distribution P2, and we write P2 to be the current P2 and P2 prime to be the updated P2 after that stage has been performed. So how do you update P2 to P2 prime, right? What you do is you just change the counting scheme, right? So essentially, because in this in the T's stage, player 2 chooses the action A2, we need to increment 1 on the weight of A2, right? If you apply this update rule, you would get something like P2 prime is T minus 1 times P2 over T plus 1 over T times whatever the whatever the vector that corresponds to A2, right? So I use chi of A2 to denote this vector. So a chi of A2 is the characteristic vector of A2. Essentially, it's a 0, 1 valued vector. At the level of at the position of A2 is 1, and at the position of any other action it would be 0, right? So this is a 0, 1 characteristic vector, right? When we want to update the belief P2, we do this essentially as you take 1 minus some sort of small value alpha, which is between 0 and 1. And in particular, in this case, alpha should be 1 over t, but I'm just writing it as alpha. So it's 1 minus alpha times P2, which is the original belief, plus alpha times gamma times chi of A2. Right, so this is how we update the belief, and you can see that the new belief is a linear combination of P2 and the action A2. Right, so that's just a linear combination of these two. The expected payoff of player 1 in this case would then be a linear combination of the expected payoff for actions assuming the opponent is adopting A2 and assuming that the opponent is adopting P2, right? So there are two cases. Either the opponent adopts P2, we get this expected payoff with the weight of 1 minus alpha, and then if the opponent adopts the action A2, then we also get expected payoff with the weight of alpha. Right? So if I add this up, that will be the expected payoff of player 1 at stage T plus 1. But now, because of the fact that A1 has been played at stage T, this means that A1 must be a best response to the previous belief P2. Right? So this means that this value of F1 of A1 with P2, that is the optimal value. Right? And also, because we know that A1A2 forms a strict Nash equilibrium, this also means that A2 is the best response to the action A2 of player 2. Right? So this also means that F1 of A1 and A2 is also maximum. Right? And if you have both of these two factors maximum and you take the linear combination with weights alpha and 1 minus alpha and you sum it up, then the resulting value will also be optimal. Right? So therefore, A1 is going to be a best response to the updated believed strategy P2 prime of player 2. Right, so that's from the point of view of A1, and similarly you can do exactly the same reasoning from the point of view of A2 to conclude that A2 is the best response to P1 prime. Right, so in this sense, A1, A2 will be played for another stage. But if that's the case, then A1, A2 will be played for a third stage, a fourth stage, and from now on, the players would just fix A1, A2 as their actions. So that finishes the first direction, right? If they have a strict Nash equilibrium in the stage game, then that will be the steady state of fictitious play in the repeated game. And from the reverse direction, we assume that we get a steady state of the repeated game, right? And then we want to conclude that steady state, which is a pair of actions, will actually be a Nash equilibrium in the stage game. So suppose the play stabilizes at a pure strategy profile A1, A2, then if you think about it, when that's the case, then the player will infinitely many times play A1, A2, A1, A2, A1, A2. So eventually player 1's empirical distribution about P2 will concentrate on A2, which is the accurate belief. So the probability that player 2 plays A2 looking from the point of view of player 1 will tend towards 1. But if A1 is not the best response to A2, then in this case, eventually player 1 would know what A2 would player 1 would know what player 2 would do, which is just to play A2. Then player 1 will eventually deviate because there will be an action which gives player 1 a better payoff. And that contradicts the fact that this play stabilizes at A1, A2. Right. Similarly, using the same argument, A2 is also a best response to A1. Right? And therefore, A1, A2 are best response to each other, and it is at Nash equilibrium. Right? So this shows that whenever we have fictitious play, and suppose it stabilizes at a certain behavior, and this behavior are pure strategy. So basically, the agents 1 and the agent 1 and 2, they both fix their actions indefinitely, then this pair of actions will form a Nash equilibrium. All right. That's the positive side because it essentially validated the reason behind choosing fictitious play as the learning rule. Although it's very, very simple, it's able to generate dynamics that allows the agent to eventually stabilize at Nash equilibrium. But there is one thing that we have to be careful about is that the requirement that these strategy profiles are pure. So also on the downside, it means that suppose the stage game has no pure strategy Nash equilibrium, we know that there are lots of such games, then fictitious play does not really generate a steady state. Right, because a steady state inherently has to be a pure thing, right? Because it's saying that this action will be stabilized, so both agents would choose the same action from now on. But if there's no pure strategy Nash equilibrium, then this means that the behavior of the agent would never be fixed. Right? Let's look at this example where we have the matching penance game. Remember, that's the example of a game with no Nash equilibrium, with no pure strategy Nash equilibrium. Of course, there's a mixed strategy Nash equilibrium. We also covered that the mixed strategy Nash equilibrium is 0.5 and 0.5. This means that the players try to confuse the opponent by only playing half of the time head and half of the time tails. And this is especially applicable to this infinitely repetition scenario, right? And now suppose that both players will follow fictitious play, and suppose there are some arbitrary initial weights that are assigned to these actions. Say the weights for W1 at the head is 1.5, for tail would be 2, and at W2 this weight for player 2 at head will be 2, and at tail will be 1.5. Right. And now suppose that with these initial weights as the initial beliefs, the agents are making their own decision about what to play in each stage. So at round 0, we have these beliefs, 1.5, 2, and 2, 1.5. And now the players enter the stage, and from the point of view of player 1, he believes that remember player 1 wants to match the penny according to the payoff matrix above. Player 1 wants to match the coins, and player 2 wants to unmatch the coins, right? So according to player 1's belief, player 2 would want to play tail more likely than head, right? Because tail has a weight of 2, whereas head has a weight of 1.5. So that means, from looking from the point of view of player 1, playing tail will be more likely to win the dollar. Whereas from player 2's action, we see that because he believes that player 1 will more likely to play head with weight 2 and less likely to play tail at weight 1.5. So player 2 wants to play tail because that's different from what he believes that player 1 would take. And in this way, he believes that he will have a higher chance of winning the dollar. Right? So both of them in the first stage will just play tail and tail. Right? But what's the consequence of that is that because player 2 played tail, looking from the point of view of player 1, this will essentially confirms the prior belief that player 2 is more likely to play tail, right? So we actually add 1 to the weight of tails, and now player 1's belief becomes 1.5 and 3, whereas in the case of player 2, actually what happened in that stage is different from his prior belief, which was 2 and 1.5. So he needs to add 1 to the belief that the first player would like to play tail. So now his belief become 2 and 2.5. So now you can see there's a switch in the belief now, because player 2 now thinks that player 1 will be more likely to play tail. So in the next stage, player 2 will play head instead of tail, because you want to always be different from player 1, whereas player 1 will stay to keep playing tail because he believes that player 2 will still play tail, right? So you can see that player 1 in this iteration make a wrong decision, and player 2 makes a correct decision. So player 2 take away this dollar, and this process go on and on, repeated to infinity. But one thing that we can observe is that it seems like eventually the players will not stabilize on certain action. They just keep changing from TH to HH to HT to TT and iterate in this way. And in fact, if we repeat it for enough number of rounds, if you develop the program to simulate the situation, you will be able to see that eventually the empirical distribution of each player will converge to 0.5, 0.5. What actually means that essentially the players are actually playing at their optimal strategies. That's just that strategy is a mixed strategy. So when we look at the actions adopted by the agents, they do not actually converge. But if you look at the empirical distribution, basically their belief in fact converges, and it converges to a Nash equilibrium. So this is actually very, very good, because obviously we would not be able to see the Nash equilibrium from the perspective of the action if the agents are playing their mixed strategies, but the belief essentially captures the mixed strategies that are adopted by the agents. Right. So the next theorem says exactly this: if the empirical distribution P1, P2 of players' strategies converges in fictitious self-play, then these distributions converge to a Nash equilibrium of the stage game. Right. So far everything has been good. If we have pure strategy NE, then fictitious self-play arrive at that Nash equilibrium, and if fictitious self-play have a steady state, which is a pure strategy, combination of pure actions, then that steady state will correspond to a Nash equilibrium of the original game. But if it doesn't, then we can be relatively sure that if the empirical distribution stabilizes, then we can be relatively sure that this stabilized empirical distribution would be the mixed strategy Nash equilibrium. So this is a really good thing that connects our theoretical analysis of the game, namely those solution concepts that we designed, with the actual dynamics of the plays of the game. Right. So why would this theorem be true? Well, I'm not going to prove it formally, but it's actually quite intuitive. So suppose we have P1, P2 converges to some strategy profile sigma 1, sigma 2, and then the player 1's belief about player 2 eventually converges to sigma 2, and player 2's belief about player 1 eventually converges to sigma 1. So if sigma 1, sigma 2 were not a Nash equilibrium, then the player would eventually deviate and change the mixture from sigma 1 and sigma 2. So as long as this stabilizes, then we know that it's definitely a Nash equilibrium. Right. So that's the positive news. Let's look at this case when we have anti-coordination game. We have AA being 0, 0, BB being 0, 0, and AB and BA being 1, 1. Right. So the goal of both of the player is so that they have mismatch in their actions. And assume that we adopt initial weight 1, 0.5, 1, 0.5 for both agents. Then we play this game, right? When we play this game, you see that the agents have their beliefs, and then according to the beliefs, they're making actions. They're making the decisions to play the next stages, and if you run this for enough number of times, you'll be able to see that the beliefs of both of the player will actually converge to 0.5, 0.5. So this seems like a very good thing, because like what we said in the last theorem, the beliefs will eventually converge to the mixed strategy Nash equilibrium. But there's something odd here. Right? If you examine it closely, if you look at the actions adopted by the players, they were playing BB, AA, BB, AA forever. Right? They alternate between BB, AA, BB, AA. So according to the matrix, the player will actually not get anything. Right? They will just get 0. Right? So this means that even though the beliefs of the agents were actually correct about the mixed strategy, and they're actually adopting the strategies according to their beliefs, and the beliefs is absolutely correct, nevertheless, these agents were actually playing, in a very suboptimal way. Right, because the actual outcome, the actual agent, the actual actions that they adopt would not give them any positive payoff. Right, so that's a weird thing, but it can be a reality in the agents playing certain games. The next question will be the harder one to tackle, and in fact, I'm not going to prove the next theorem for you. So we've talked about, if the fictitious self-play eventually lead to a convergence on the beliefs for the players, then that beliefs will be the mixed Nash equilibria. Right? This is all assuming that the belief will converge. Right? We do not have the other direction, saying that if there's a mixed strategy Nash equilibrium, it will definitely converge. And in fact, that does not hold in general. However, we can prove for some fairly natural and large class of stage games, this holds. So the convergence can be guaranteed for a number of classes of stage games. For example, if the stage games is a zero-sum game, right, then we can guarantee that the fictitious self-play will eventually converge in empirical distribution. Or if the stage game has a unique iterative elimination equilibrium, then fictitious play will converge. Or if the payoffs in all of the bimatrix of the payoff matrix, right, are all distinct, then the fictitious self-play will converge. And fourthly, if the game is a potential game, which is a concept that we did not cover, essentially it being a potential game is that the local payoff are somehow described by a global function. And this will be a special type of normal form game. And if that's the case, then we know fictitious self-play will eventually converge in empirical distribution. So these are the cases that we know. But can we find an example where fictitious self-play does not converge? I'm going to give you this very interesting example. It's also very, very simple. So this is a game that we are all familiar with, rock, paper, scissors. And you can come up with this matrix, this payoff matrix. So everybody has three options to play: rock, paper, and scissors. And if they play the same action, both of them will get zero payoff. So they just have a draw. But of course, paper wins over rock, scissors win over paper, and rock wins over scissors. So you have 0, 1 value for these other combinations. If you do the analysis, you would see that there's a unique Nash equilibrium of this game, which is 1/3, 1/3, 1/3. So if just like in the matching tennis game, the player, if they want to play in an optimal way, they would make the opponent not aware of what action he would choose, right? So he would just choose the same probability for either one of the paper, rock, and scissors. In this way, that's the way to guarantee the maximum payoff. However, if you adopt a fictitious self-play to this game, so if you start with some initial beliefs, and if you assume that both of the player will follow fictitious self-play, so hopefully they will learn, right, through the interaction and through observing the opponent's strategies. The game actually does not converge, right? It does not only diverge in terms of the actions that the agents play, but also diverge in terms of not converge in terms of the beliefs that they hold, right? So there's no actual, if you look at the sequence of empirical distributions held by the players, it does not tend to any fixed vector, right? So why is this? I would encourage you to take a moment and think about the situation and actually sit down and draw the play. And we have to fix a certain initial belief. And in this case, I assume that the player 1's belief about player 2, the initial belief will be 0.1, 0.2, 0.3, and player 2's belief about player 1 initially will be 0.2, 0.3, 0.1. Right, and then very easily we will be able to allow the agents to make decisions, because, for example, in player 1, after making this observation, he thinks that player 2 is more likely to play Caesars, and therefore in the first stage he responds with rock. But player 2 thinks that player 1 would more likely to play paper, and so player 2's action will be responding by Caesars. So in this case, player 1 actually made a right prediction, and therefore he wins for one round and increase the belief on Caesars by 1. Right? Whereas player 2 realized that he has made a wrong decision, so the belief is wrong, so he updates the belief by increasing rock by 1. So now the new belief is 1.2, 0.3, and 0.1. In the second stage, they will play corresponding to this updated belief iteratively. But what you can observe is that, of course, first of all, the action of the player, they alternate. But also you can see that there are some big swings in terms of the beliefs held by the players. I've actually played the game for a very long time until stage 109, and I did not describe all of the 109 stages to you. I just written down a number of very important stages. So without illustrating all of these stages, I'm going to somehow describe using a very high level language about what will happen to this game. So the game will actually cycle through this a number of iterations. So it will stay stable for a number of stages, and then one of the players will deviate. So if you're an outsider, when you look at the game, it will be quite boring, and it will become more and more boring because there are not many stages where the players change their actions. You can see from the previous table, for example, starting from from stage 4, where the player 1 would choose Caesars and player 2 would choose papers, then they will keep playing in this way for 4 rounds, so 4, 5, 6, 7, until at stage 8, where player 2 made a deviation to change from papers to rock. Right, and then from now on, they will keep playing Caesars and rock for 8 stages until player 1 finally made a change from Caesars to paper, and at stage 15, the players will play paper and rock, and then they will keep playing paper and rock for about 11 stages. Until player 2 make a move, and then they keep doing that. So on the right hand side, you see that those stages that I list on this table are exactly those stages where the players deviate from what they have been playing. And you can see that the period of them keeping the same actions gets longer and longer. Right? So this is a result of fictitious self-play. So we call a stage a deviation stage when one of the players deviate from the previous action, and these stages that I illustrated in the table, so 2, 4, 8, 15, 26, 44, were deviation stages. At any deviation stage, one of the players has a wrong belief. It then stays in this wrong belief for a while before realizing it and switching to the right belief. Right. So whenever there's a wrong belief, but because it's so wrong, it would just stay in that way for a period of time until it realizes that this is the right belief. But the consequence of that is that during this period, although it's a wrong belief and he's playing according to the wrong belief, this helped to consolidate the opponent's belief about this player. But when this player eventually deviates from this action, all of the consolidated belief of the opponent becomes wrong, right? And it would just take the opponent even a longer period of time to realize that that was a wrong belief, right? So this whole thing enforces, indicator some sort of a positive feedback, right? So iteratively, the period of time when the person holds a wrong belief becomes longer and longer before realizing that it was a wrong belief. So that's why we see this big shift, this big swings on the beliefs of the agents, and it never stabilizes to any fixed value. So to analyze it even more closely, we let Ti to denote the weight difference, the difference between the weights of the actions, between the wrong belief and the right belief at the ith deviation stage. Then we can derive a rather simple recurrence relation that Ti is roughly the same as Ti minus 1 plus Ti minus 3. So this indicates that the weight difference between the wrong beliefs actually increases in an exponential way, right? And that's why the belief cycle in this way never converge, right? So that's a very interesting example which illustrates that if players follow fictitious self-play, it's not necessarily true that eventually we're going to converge to a single set of beliefs. Right. And that finishes our class for today. We've introduced the paradigm of learning in a multi-agent system context. We describe, in general, the new challenges that are faced here. And then we mainly focus on looking at the learning rules for two-player repeated games. And then we introduce fictitious play as the very basic learning rule, which assumes empirical, which basically take empirical distribution as approximation to the opponent's behavior, and it assumes basically stationarity assumption for the opponent. And we've also discussed the connection between steady states and Nash equilibria of the stage games in fictitious self-play, but also we discussed convergence issues of fictitious self-play, and in particular we'll look at an example where fictitious self-play does not lead to convergence of the empirical distribution. Right. So that's for today, and I'll see you in the next lecture.